So welcome back. Let's talk about Elec271 part 10 and 11. Introduction to the feedback 1, 2. So it's the thing we are going to make here is that how do we make near to ideal amplifier? So introduction to feedback, the summary we have talk about the device electronic model hybrid pi used to analyze the amplifier configuration, common emitter, common collector, common base. The common emitter we emit aggregation and differential amplifier looked for the DC bias techniques for the IC-based circuit, current mirrors, current source, analyze for the frequency response of amplifier using the equivalent circuit. For example, the FT, the AV, and the high bandwidth configuration, the common base, cascaded, filed transistors can use similar approach, but the model is different. The step response for amplifier. So the second part is about the feedback. So what is negative feedback? What happens? It has applied to amplifier, also converted to a control system. So why the negative feedback is important? Because transistors are such a poor components that which need the negative feedback to allow us to build more precise amplifiers using the cheap and poor tolerance components. So what we do is that's the example of the poor amplifier. It's just like, for example, the initial value is one. The initial value is for beta 1, beta 2, beta L, beta J is around 100. So double the beta we have around the 200, and what we change it, we will level up, we level down. We're going to see that this is going to change a lot in the amplifier, which means that they are very sensitive to the change the current configuration. So therefore, we are going to build a better amplifier, which means that the forward single signal path and the feedback path, while a feedback resistor RF1 and RF2. So don't worry about the detailed circuit operation at the moment. We're going to look at it just later. And so for example here, so the initial value is beta 1 is 100. We double it, it's around the 0 point. The change here is very small based on feedback loop. It is worth noticing that this one is actually we are forwarding back the output, right? We are forwarding back the output, which means that we are forwarding back the output, which means it is our voltage amplifier. The forward back signal, it is the voltage signal, and so therefore it is easy to see a thing that we are going to build amplifier. It's very easy to build amplifier with a lot of gain, but we are going to build some feedback to stabilize it. So the thing is that for the advantages of our negative feedback, that the negative feedback reduces the sensitivity of the gain on the parameter of the amplifier, such as the transistors current gain. The negative feedback allows us to gain at any value we want. Negative feedback increases the bandwidth of the amplifier. The negative feedback reduces the distortion. Negative feedback allows us to adjust the input and output impedance of the amplifier. But these do not come with free. For example, we are going to reduce the gain of the amplifier always. And once the certain frequency ranges can be that negative feedback changes from negative to positive with cascaded results. Positive feedback increases the gain of the amplifier, and amplifier may be converted to an oscillator that is no longer used as the amplifier. So does that mean that it is that means oscillator is like this something? So this is 211 or 211, 271. So it's discussion board. dot trend. Just like and we are going to introduce the feedback. Another feedback loop is that it is just take a look at where do we find the feedback loop. The feedback loop is just here. It is this one. This is the feedback loop. This is the feedback loop. It is connected to the output. And this one is not a feedback loop. This one is changing. This is the current. This is the current. So it is not. This is not from the output node. It is sample. What you mentioned that they are sampling. What do the sampling mean here? And then let's look at the. So the lecture said that we are actually sampling from here to here, sampling the current, but do not know what that means. So let's introduce to the negative feedback, which means that the result is gonna to show that this kind of gain it is good. Okay, so what makes the amplifier AI stable? Actual answer is basically the way in which the feedback is applied to answer the question. We need different type of amplifiers. For example, we have the voltage amplifier, the current amplifier, the resistance, transresistance amplifier, transconductance. The transresistance amplifier is measured in ohms. The transconductance amplifier is measured in sigma. The feedback can only stabilize one of the gains for an undual amplifier. What makes the amplifier different? When it is possible to describe the amplifier as a voltage amplifier rather than current amplifier. So it actually varies. So the thing is that what we expect from a good voltage amplifier is that overall the voltage gain from the source to load should not vary too much in the change of the RG or RL, ideally or not. So experimentally we could have this register to see if the voltage gain remains a constant. If it is, we are having a good voltage amplifier. What makes a good voltage amplifier? So that is a very good question. So the amplifier will be good voltage amplifier if its equivalent circuit look at a model below. R in is great and R out is small. So what does that mean? So look at a voltage amplifier. A voltage amplifier that we in and so we want the voltage, right? We want the voltage to go here, right? Therefore, we want R0 to be small. So because we do not want R0 to take much voltage from the kV in, and for the way in part, why do we want the R in to be great? Because the R in must be great because the voltage must be applied on R in, therefore it must be great to hold this voltage. So that's very great, and it is worth noticing that there's no capacitors, therefore there's no way about the frequency response. That is the good thing. And we can connect the load and the source to the amplifier, so let's prove that. So let's say that the way out, okay, for the way out, we are connecting here. This is the way in. So actually, this is called way in, but in terms we are connecting to a dominant voltage source, so we regard as the VG as our target. Okay, and this is the way out, which is the parameter we are going to A way. Okay, A way is called the way out divided by VG. Okay. So let's look at what are the expression for the way out. Way out is like a differential, right? So this is RL divided by RL plus RO times K way in, right? This is great. And for the way in, it's R in plus R in plus divided by R in plus RG. So that's also great. So now we are going to apply this formula. We are going to have the A way is called RL times K times R in divided by R0 plus RL times R in plus RG. So that means that the A way does not depend on the RG and RL. So this means that as it's required, so it does not matter. Okay, so that is stable. Okay, that is stable. So an ideal voltage amplifier is have R in equals infinity and R out to be 0. That's great. Okay, and so the reason why is that R in is infinity, so that is infinity, and R out is 0. R out is 0. R out is 0. R out is 0. So this is 0. Yeah. So it's the denominator should be great and the denominator should be low. And we can connect the load and the source to the amplifier as follows. For example, we can. Now let's look at the. So we connect the load and source to amplifier. Oh, let's look at that. That's very interesting. Okay, so we can to a source and amplifier. Okay, so this is previously is a voltage amplifier. Now it is a current amplifier. The current amplifier here we have the I in and the corresponding K I in, and let's assume the AI is equals to IR divided by I in. So the thing is that let's connect it as long as this is a voltage in as the input. So we are going to convert it to a Norton voltage equivalent circuit. So that is very true. So this is IG. We are going to this IG. This is a Norton equivalent circuit. That's great. And so let's look at that. So we also apply the division of the current. For the way I out is equal to, since it's an inverse proportional, so therefore I out is going to be R out divided by RO plus RL divided by I in, right? So K I in, right? K I in. So that's great. And for the I in for the input part, we can also say that I in is going to be IG so I in is going to be the Rg divided by Rg plus R in times R in Ig, right? So that's great. So now let's look at the I out. So okay, let's look at I out. So I out, we're going to apply them back. So I out is going to be this. So it's R0 divided by R0 plus RL times K times R in. So that is Rg times Rg plus R in times Ig. So in order to make the output, the gain as large as possible, we would like to make the Ig out R0 Rg, right? So Ig, right? So we would like to make Rg as large as possible, right? The Rg. So the Rg, Rg 加 in，that is very intuitive. So we want to make it higher. So out should be infinity and R in should be 0. So the homework can you generate? And this is the first part. The second part is for the 12. Let's look at this. It's very simple. So generic amplifier type feedback. The ideal voltage amplifier AV is equivalent to VR divided by V in equivalent circuit. That's like the Ri is approach to infinity, R out is approach to 0. And for the current amplifier, we are going to make this to be infinity 0 to, and this is going to be infinity. So which means that we would like all of the current going through this way and none of the current going through this way, all is going to that way. And what if it's a trans resistance, which means that it is a current-driven voltage source. So it's like a V divided by I, so it's a current-driven voltage source. Okay, so it is a voltage source. Therefore, this one must be our output. This is the output means trans resistance. Yeah, that's the voltage divided by current. And if it is a resistor, okay, if it is a resistor, that will show you that resistor. So this is R out should be as little as possible. So this is current here. This should also be as little as possible. So transconductance means it's very simple. Is what we mean is just to make the transconductance. Transconductance means this is I divided by V, right? So this is voltage. So this one must be as great as possible. So because this is the voltage that we rely on, right? And I here means the I here. The I here is just the I here. The I here is the I here. The I here is the I here is. The I here is just I divided by V, so it's I divided by V. I divided by this is this is I, right? So this is also infinity to make all of them going to go there, and we're going to have some more questions like here. So where the source has a high impedance and the load is very large, please build a suitable amplifier for good matching between the source and load. Sketch the system diagram with the appropriate equivalent circuit for the source. And so what if the internal impedance of the load is large? Then it must be internal resistance of a load is large. It must be a current source, right? And what if it is a current source? Current source. What if it is a current source? Then the load, the input resistance, the load is large. The load is large. So now we replace that with然后这个是 so this is Ri, and this is the so this is RL R0. So that is R0. That is R0. Why do we put the R0 like here? Source has a high internal impedance, and the load is large resistance. Choose a suitable amplifier type to ensure good matching between the source and load. Hence, sketch a system diagram with the appropriate equivalent circuit for the source and a generic amplifier type, amplifier equivalent circuit. Source has So what if the load is a very large resistance? It must be a voltage. So it is transconductance. I think this out should be 0, right? Trans resistance 对，应该是。 quick calculation for an ideal voltage amplifier, just like side, we have the V out divided by V in for circuit poles that RG equals to 750. IL is 3.1 kilo ohm, and the amplifier is perfect. AI is 8.58. So, that is very simple. What we need is just to put the resistance here and put the sensitivity. This is 350. Yes, this is. So what we need is just to put the voltage here. Since it is V out divided by V in, this one should be infinity, and this is the voltage gain. So this is very simple. Let's look at that. V out be V in, RG equals to, and IL is 3.1 kilo ohm. And the amplifier is perfect current amplifier. So AI is that. And I have a question. How do we make I'm not sure, but generally I just put it here. and here. So since it is a voltage gain, what do we have? The output resistance should be infinity, but the input resistance should be 0, right? Therefore, this is 0 and this is infinity. So as is the ideal, what we have is I. So we will only leave out to be something like that. So it is very simple that we put the RG, we put the so in this case, so this is 8.85 I in, right? 8.85 I in, right? So this is so that is the VG. So the VG is just VG I in equals to VG divided by 750, and V out is going to be 3.1K times 8.58 I in. So therefore we have V out. So 3.1K times 8.85 times VG divided by 750. So in order to have V out divided by VG, so that is 3.1K times 8.85 divided by 350. So that is the case, okay? And in that case, we can calculate, right? We can calculate. But I do not have Mathematica, but you do not need Mathematica. So that is K. So you can approach, right? So this is most 35, right? That's great. And we have quick calculation for ideal equivalent circuit 2. So we have V out divided by VG. So RG equals to 750. RL is 3100, and the amplifier is perfect. The transconductance amplifier. Transconductance means everything is infinity. So this is infinity and this is infinity. So that will be very simple. Okay, that is very simple. That is just the R out. V in equals to VG, and V out is going to be 320 times 10 to the power of 13 times 3.1K times VG. So that is just 32 VG. So that's all for today. Thank you very much for comments.